Hello, student. Uh, So I think this is your third lecture. So here we are going to discuss about some sequential and logic circuits. Okay, let me share my screen. Okay, so still we are in LO1. Okay, learning outcome one. Learning outcome one. Okay, so we have learned how to simplify a Boolean expression. Okay, using McCluskey method. Okay, so now we want to discuss about some sequential logic circuits. Sequential logic circuit. Okay, there we hope to discuss mainly about counters and registers. Okay, registers. So to start these topics, okay, I hope you need to have the basic knowledge of flip-flops actually. Okay, flip-flops. So these flip-flops are actually the building blocks. We can say that these are the building blocks. Okay, building blocks of uh, almost all sequential logic circuits, or many logic circuits, many sequential logic circuits, many sequential complex logic circuit. Okay, such as counters and registers. Okay, uh, so we need to have a prior knowledge uh, about flip-flops. Okay, so let's try to refresh our memory on these topics, flip-flops. Okay, so and you know that flip-flops is we can say that it is a basic sequential logic circuit. It is the most basic sequential logic circuit. Okay, sequential logic circuit. So you already know what is sequential logic circuits, no? Uh, we normally refer to sequential logic circuits if the output of the circuits depend on the previous output. Okay, so that is a sequential logic circuits, no? Okay, so it is a with memory system actually. Okay, so we can say that sequential logic circuit is a memory system with memory system. Okay, and the present output, okay, present output depend also on the past output. Okay, past output. So those are the sequential logic circuits. Okay, and if you consider the flip-flops, okay, you already know that these flip-flops can be uh, construct using logic gates, basic logic gates, such as AND gate, NAND gate, like this, and OR and NOT gate. Okay, and commercially these are available as a chips. Okay, I think you already know that we have used those in last in previous session, previous interaction session in the lab. Okay, uh, so so we can say that flip-flops is small scale integrated circuit. Okay, I think you know that integrated circuit, about integrated circuit. Okay, integrated circuits means components are integrated to form the circuits. Okay, So it come as embedded system. Okay. So those are called integrated circuits. Actually, these counters and registers are also integrated circuit. Okay. That is why I want to tell you about the integrated circuits. Okay. Uh, so I think you should have the basic knowledge about the integrated circuits or IC. Okay. So uh, you know that, I think you know that what is integrated circuits. Okay. So normally in a normal circuits, okay, we have transistor, resistors, and diodes. Those are separately. Okay. Those are separately. We have separate component, separate basic component, electronic component, such as transistor, resistor, capacitor, inductors, diode. Those are separately. Okay. But integrated circuit, okay, these are uh, these are uh, what is called, these are embedded, or these are included in one chip. Okay. So you can't see separate connection between them. Okay. So it can be seen as uh, one chip. Okay. You can't see separate uh, separate component in it. Okay. So there are many advantages and disadvantage of this IC integrated circuits. Okay. I think you have learned them in your previous session. Okay. And this IC we can uh, again divide into many uh, many parts depending on the uh, component. Depending on the included components, number of components. Okay. For example, we can say that uh, very small scale integrated circuit. Okay. Small scale integrated circuit, and medium scale integrated circuit, large scale integrated circuits, like that. Okay. So I think this flip flops is flip flops belongs to this category. Small, very small scale integrated circuits. Okay. Okay. Because it has only 2 or 3, maybe less than 10 uh, logic circuits, logic component, basic logic gates. Okay. So these are very small scale integrated circuits. Okay. uh, and uh, So some maybe, so I can't remember the exact number of, so I think there is a definition. Okay. There is a definition with the components, number of components. Okay. For example, if the number of component is less than 10 component, it is called very small scale integrated circuit. Okay. Maybe the component between 10 and 100, it is called small scale integrated circuits. Okay. Maybe 100 to 1000 or 10,000, it is medium scale integrated circuits. Okay. So anyway, I can't remember the exact number. Okay. But you can check the internet. Okay. So you can see the proper definition. Okay. What is the proper number of components which these integrated circuit include. Okay. So basically what I want to tell you is that the counters are medium scale integrated circuit. Okay. MSI. Okay. The counters and registers are belongs to this category. Okay. So that is the things what I want to tell you. Okay. So I think you should have the basic idea about these things. Okay. Okay, let's again come to the flip-flops. Okay, we need to refresh our memory on flip-flops to continue. Okay, so I hope that we have two basic flip-flops. Okay, one is RS flip-flops, Another is a JK flip-flops. Okay, JK flip-flops. And there can be many configuration of these flip-flops. Okay, and there can be many configuration, and they are combined in different way to form other type of flip-flops also. Okay, so basically we should have at least uh, the knowledge about this RS and JK flip-flops. Okay, uh, so you know that there are many configuration. As I have told you that there are many configuration of these flip-flops. Okay, so I think one configuration is, I think you know that we referred as clock flip-flops. No, clock flip-flops. Okay, actually clock flip-flops means, okay, the flip-flops is operating on a clock. Okay, so that is referred as clock flip-flop. Okay, so if I explain it somewhat more, okay, so you know that, okay, let's take example. Okay, so let's take RS flip-flops. Okay, so I think there is a function table for this RS flip-flops. Okay, okay, so we have two inputs. Okay, we have two inputs, S and R. Okay, and we have the output. Okay, so output we normally referred by Q n plus 1. Okay, so n plus 1 means the present output. Okay, Q n plus 1, this is the present output. Okay, and Qn will be the past output. Okay, so this is the notation. Okay, this is the notation for the output, present and past output. Okay, because I already told you that flip-flops, the output is depend on the past output. Okay, so we have to consider the past output bits also. Okay, so if I draw the function table, okay, so it like this. Okay, so I have write it somewhere because I can't remember these function tables actually. Okay, actually I don't want to remember this function table also. Okay, it is very simple. Okay, only 4 status are there. Okay, but I think you no need to remember. So if you want to use this, I can in the exam. So I will give it. I will give this function. Okay. So you no need to remember this, but you should know how to apply this. Okay. To solve or analyze the circuits. Okay. So that is the requirement. Okay. So I don't want these things in your you no need to remember these things. Okay. For the exam. Okay. Uh, so it will like this. Okay, if we have 0 0, we have Qn, that is the past input. Okay, if the S and R is 0 0, the we have the output as the past output Qa. Okay, if it is 0 1, it is 0, and if it is 1 0, it is 1. If it is 1 1, that that combination is not allowed. Okay, this is not allowed. So this bit combination is prohibited actually. This is a forbidden combination. Okay, in SR flip-flops, we have a not allowed combination. Okay, in SR flip-flops, we have a forbidden combination, bit combination. Okay, so 1 1 is not allowed here. Okay, the output we can't define. It is not stable actually. Okay, at that time the system is unstable. Okay, so actually for this, so this is the function table for SR flip-flops. Okay, actually this is for active high flip-flops. Okay, so you know that when we are talking about digital circuits, we are come we are coming across in two terms. One is active high, okay, active high, and this other is active low. Okay, so we have these two configure these two. So this is actually we have discussed this in our interaction session. Okay, so these are the way to give the input. Actually, these are the way to define the voltage level, high and voltage level. Okay, so this is for active high flip flops, RS flip flops. Okay, so it is normally denoted like this. Okay, so we have this is the flip flops. Okay, and we have two input S and R. Okay, and we have output Q n plus 1. Okay, and if it is a clock flip flops, the clock pulse also should be there. Okay, and this should be the clock. Okay, this should be the clock. Okay, and this is the block diagrams for the active high RS flip flops. Okay, active high RS flip flops. Okay, active high RS flip flops. Okay, and there is another type, active low flip flops. Okay, active low RS flip flops. Okay, so there we have to put a NAND gate, sorry, not gate, to the input. So we denoted it using a circle. No, this is a not gate. Okay, so this will be S and R, and the clock pulse should be there. Okay, and please remember that we don't put not gate to the clock. Okay, so clock is same as in this case. Okay, and we have the output, and that is Qn plus 1. Okay, so this is the uh, diagram or block diagram for the active low flip flops. Okay, flip flops. Actually, we have two function table for the two cases. Okay, but if you basically have one function table for active high, you can derive this for the active low flip flops also. Okay, so I am not going to explain this any more deep, because you have already learned these things. Okay, because we have another things to learn. Okay, so if this R is there, Qn plus 1 is there, you can see that here uh, the S and R inputs are given by inverting, no, using the not gate. Okay, so all status will be inverted. Okay, for example, here 0 0 is undefined. Okay, so 0 0 is undefined. Okay, undefined. Here 0 0 is Qn and 1 1 is undefined. But if you put 1 1, the input should be again 0 0. In this port, in this line, it will be 0 0. So 0 0, in this case 0 0 is undefined. Okay, and if it's 0 1, here it is 0, here it should be 1, and if it is 1 0, this is 1, and here it should be 0, and if it is the 1 1, the status should be Qn, passed input. Okay, so this is the function table for active low RS flip flops. Okay, active low RS flip flop. Okay, so if you have one function table, you can get the other one. Okay, Uh, okay. Uh, Now, so this is the function table for the RS flip-flops. Okay. So clock RF flip-flops means, okay, uh, we have to give a clock to activate the output. Okay. So that is the idea. Okay. So clock pulse is like this. Okay. Clock pulse will be like this. Okay. It has 0 level and 1 level. Okay. 0 and 1 level. Okay. So this is 0 level and this will be the 1 level. Okay. Level 1. Okay. So you have 2 levels. Okay. That is the normal way to give a clock. Okay. 0 and 1 pulse rate. Okay. So you can see that, okay, I think you can remember that if this is 0, the clock level is 0, the output is not changed. Okay. So at all the time, output will be the passed output. The present output will be passed out. Okay. So if the clock is 0, you always have the passed output. The output not change. You have the passed output. Okay. And if the clock is 1, the output will be changed. Okay. Actually, if the clock is 1, this status will be active. Okay. If the clock is 1, this status will be active. Active. Okay. So if I put the clock here, if the clock is 1, uh, the flip-flops give the output according to the input. Okay. But the clock is 0, the flip-flops doesn't give any output. It will keep the output as same, okay, as Qn. Okay. So that is the idea. That is the clock flip-flops. Okay. And when we are talking about clock, okay, clock flip-flops, I think you have already know these things. Okay. We have two types. Okay. One is level triggered clock flip-flop. Okay. Level triggered clock flip-flops. And the other type is edge triggered clock flip-flops. Okay. Edge triggered clock flip-flops. Okay. So, uh, so what does mean actually? So level triggered means the output is changing at the level. Okay. So that is the idea. Output is changing at the level. So okay, I already told you that the clock pulse. So this is a clock pulse train actually. So this is a clock pulse train. It is a pulse train. Okay. We have number of pulses. Okay. So this is a pulse train. Okay. Or we can say that it is a clock train. Okay. Or clock pulse train. Okay. So you know that we have two levels, 0 and 1. Okay. Clock triggered means, sorry, level triggered means the flip-flops is working according to the levels. This level, this 0 and 1 level. Okay. 0 and 1 level. So as I told you, if the level is 0, the flip-flop will not change its output. Okay. It will keep the output as same as Qn. Okay. If the level is 1, the flip-flops will change the output according to the inputs. Okay. So actually this is the function table for clock triggered, sorry, level triggered flip-flops. Okay. And actually this is the diagram for level triggered flip-flops. Okay. So it is level triggered active high flip-flops. Okay. And this is level triggered active low flip-flops. Okay. So you can see that clock is given without doing uh, any change. Okay. Clock is directly given. Okay. So this is called level triggered. Okay. We have discussed these things in the interactive session. So I think this explanation is enough. Okay. So if you can't understand, you can ask me again. Then I can explain it later in the interaction session or in a mentoring session. Okay, so you can ask. Okay, uh, but I think you have already learned these things. Okay, in your previous uh, module, digital electronics one. Okay, not digital electronics one. That is logic design or something. No? Okay, so you have one module now. You have learned one module. We have done one module before this one. Okay, so I think you have learned these things in that module. Okay, uh, okay, so that is the level triggered uh, clock input. Okay, so uh, to understand it more, okay, I will draw the mm, characteristic table. Okay, characteristic table. Okay, uh, so in the characteristic table we normally use the uh, qn status also. Okay, qn means pass uh, output status also we included to the function table, and it is referred as a characteristic table. Okay, so this is s and r we have, and we should have the clock also. We should have the clock also. We should have clock pulse also. This is clock. Okay, and we should have the qn plus 1. Okay, so you know that. Okay, you know that if the clock is so so the clock pulse will look like this: 0 1 0 1 0 1 0 1. So this is the clock levels, and we can write the input levels are input levels: 0 0 1 1 0 0 1 1, like this. And this is s. Okay, so it should be 0 0 0 0 and 1 1 1 1. Okay, so you know that if the clock is 0, if the clock is 0, the output should be qn. If the clock is 0, it is not dependent on the input. Whether the input is 0 0 0 1 1 0, in the same case, in all cases, if the clock is 0, output will not change. Okay, so here output 0, and here also the output 0. Okay, and when the clock is 1, okay, so this is for level triggered. Okay, this is for level triggered active high JK flip-flops. Okay, active high JK flip-flops. Because I am going fast because these are already done. Okay, uh, so this is a level triggered active high JK flip-flops function table for level triggered active high JK flip-flops. Okay, so this is the function table. Okay, when the clock is 0, it will have the same output. Okay, but if the clock is 1, we will have the output, the present output will depend on the input and also on the past output. Okay, so this is active high. Okay, active high. Okay, so the truth table is, so function table will be, okay, when it is 0 0, the qn is there. 0 1, okay, so I will use another color. Okay, qn is there. Okay, and when this is 0 1, okay, 0 1, the 0 is there. 1 0 1 0, if it is 1 0, 1 is there. And if the 1 1, I'm sorry, if it is 1 1, if it is 1 1, this is not defined. Okay, so this is status is not allowed. Okay, So this is not defined. If the S and R inputs are 1, 1, this is not defined. Okay. So this is the function table. Okay. And if I draw the truth table, okay. So I told you that we have to consider the sorry, not truth table, characteristic table. Okay. I already told you that we have to consider the Qn status also. So Qn will be 0, 0, 0, 0, and 1, 1, 1, 1. Okay, correct? Sorry, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. 1 also should be 8, no? 1, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these are the whole combination. Okay, so you can write it very easily, no? Okay, so you can know that. So you know that if the clock is 0, the out qn plus 1 be 0. Sorry, if the clock is 0, qn plus will be the past output qn. Okay, so you know that in the we can quickly fill. Okay, so you know that now qn is 0, so this one also will be 0. Okay, okay, and here also it will be 0, and here also it will be 0. Okay, because the input is 1. Okay, and we have to write the other combination also here. Okay, so I think your reference book has these things. Okay, so you can refer the reference book. Okay, to get if you need a more understand. Okay, so this one also not allowed because that one is 1, 1. Okay, okay. So you can see that here also we have. Okay, I will use Excel sheet. Okay, otherwise this is not easy. Okay, I can't know this table actually. Okay, so you can see that now we are talking about uh, level triggered. Okay, level triggered, level triggered, active I J K flip flops. Okay, JK flip flops, JK flip flops. Let's say that FF. Okay, and we should have the present output. Sorry, the previous output qn. That is the notation. Okay, and we have two input pin S and R. Okay, and we have the clock pulse CLK. Okay, so this is the clock. Okay, and we have the present output, that is qn plus 1. Okay, qn plus 1. Okay, so clock pulse will be 0, 1. Okay, 0, 1, 0, 1, 0, 1, 0, 1, like this. Okay, copy the cell. Okay, so this will be your clock pulse. Okay, and you have other combination for R input 0, 0, 1, 1, like this. Okay, so this is 0, 0. Okay, and this one you can write 0, 0, 0, 0 and 1, 1, 1, 1. 4 ones, no? Okay, right. Okay, so you have this combination. Okay, okay, and you have this combination also. Okay, okay, okay. So, so you know that if the clock is 0, okay, if the clock is 0, you have the previous output. So you have Qn here, Qn here, and here also clock 0. So Qn should be there. Here clock 0, Qn should be there. Okay, and you can see that again Qn here. Okay, clock is 0. Okay, okay, and here also clock is 0 Qn. Okay, and here also clock is 0. Okay, and here also clock is 0. Okay, here also clock is 0, and here also clock is 0. Okay, 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 and if the clock is 1, you have the flip-flops will be activated. No, it is in active mode. If the clock is 0, flip-flops is not in active mode. Okay, so if it is active mode, the uh, the, the present output will be changed. Okay, according to the inputs and R inputs as well as past output. Okay, okay, I think it is clear. Okay, if it is in active mode, that means if the clock level is 1, okay, if the clock level is 1, the flip-flop's present output Qn plus 1 depend on the input S and the input R as well as past output Qn. Okay, so we can easily fill this one also. Okay, if it is 0, 0, you have the past output. Okay, if it is 0, 1, you have 0. Okay, actually this is called reset. No, this is called reset status. Okay, 0, 1. S0 and R0, we called it reset status. Okay, and if it is 1, 0, okay, if it is 1, 0, it is 1. Okay, so this is set. Okay, this is set status. Okay, and if it is the if it is 1, 1, so that means it is not defined. Okay, here it is not defined actually. This is undefined. Okay, this is undefined. Okay, and this one also undefined. Okay, and uh, again you can see that the same things are repeating. If it is 0, 0, you have Qn. Okay, you have Qn, and it is 0, 1, that means it is reset. Okay, if it is 1, 0, that is set, that means 1. Okay, and these are again undefined. Okay, these are again undefined. Okay, these status are again undefined. Okay, likewise it is continuing. Okay, I think you can feel. Okay, okay, so you can see that this is the function table. This will be the function table for level triggered active high JK flip-flops. Okay, now if you want to write the characteristic table, you have to consider this Qn status also. Okay, so there are I think 16 combination should be there. Okay, 8, 1, 2, 3, 4, 5, 6, 7, 8 zeros and 8 ones. Okay, 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. Okay, then we no need this one, no? Okay, so these are the all combination. Okay, so these are the all combination. Okay, so I think we have almost filled, no? Okay, so what you have to do now, you have to put the qn plus 1 according to the past output. Okay, so you can see that. Okay, so I will use this column to put the bit value. Okay, so this is qn plus 1 bit value. Okay, so you can see that if the clock is 0, you have the same previous input qn. Okay, so here you have 0. Okay, and so here also the clock is 0. That means you have the previous bit. Okay, so that is 0 again. Okay, and here again we have a clock 0. Okay, so here also the uh, the present output will be the same output, past output. Okay, so it will be 0 again. Okay, and here also these are undefined. Okay, so we don't have any value here. Okay, so these are just undefined. Okay, put that mark, no, it is take as a function. Okay, okay, so these are undefined. Okay, and here again the clock is 0. Okay, but what is the output? The past output, it is 1, no? The past output is 1 and clock is 0. That means it not change the past output, present output, sorry. Okay, so you can see that the clock is 0. Okay, and now it has the output 1. Okay, so if the clock is 0, it doesn't change the output, no? Okay, so it will give the previous output for the present output also. Okay, so here you have 1. Okay, correct? I think you can understand. Okay, and here also you have 1. Here also you have 1. Okay, okay, and these are again undefined. Okay, these are again undefined. Okay, so it is very easy, no? Okay, and you can see that now we have the active mode. Okay, we have to consider the active mode, so you have to consider all the things. Okay, so you can see that now if the clock is 1, if S and R is 0 and 1, it will reset the flip-flops. Okay, so it will reset the flip-flops. Okay, whether the qn is 1 or 0, it will reset. Okay, that means again it reset it to 0. Okay, and here it is S and R is 1 and 0, so that is the set condition. Okay, so if you give the S and R as 1 and 0, it will set the flip-flops to 1. Okay, so it will set the flip-flops. Okay, all these are same. Okay, and I'm sorry, if they say S and R are 0 0, so you will have the past output again, so you will have 0 again because the qn is 0 in this case. Okay, okay, and if you consider this one, okay, so you can see that SNR 0 0. Okay, so you will have the present output as the, so you will have the past output as the present output. So the past output is 1, qn is 1, so again you have 1 here. Okay, so this is 0 1. Okay, that means it is the reset condition. So this will be 0. Okay, and this is again, sorry, 0 and 1 is set condition, no? 0 and 1 is set condition. Okay, yeah, set condition. 0 and 1 is set condition, so it should be 1 here, no? 0 and 1, 0 and 1, sorry, 0 and 1 reset. Okay, 0 and 1 reset. Yeah, okay, so we are correct, no? 0 and 1 reset, so we have reset the pin again 0, and we have 1 0, that means that is the set status. Okay, set condition 1 and 0. Okay, so here 1 and 0, so you have set it to 1. Okay, 1 and 0, you have set it to 1. Sorry, not set it to 1. Yeah, set. No, sorry. So you can see that this is inactive mode. No, inactive mode, this is 0. Okay, so clock is 0, so that is inactive. Okay, so it is not set or reset. Okay, I'm sorry. Okay, I hope you you will not confuse. Okay, if you have any confusion, please ask me again. I can explain it again. So this is very simple. Okay, you have to consider the bit combination only. I'm sorry, this is 0, that means it is in inactive mode. Okay, the flip-flop is inactive mode, so you will have the same output, the past output as the present output. Okay, so you will have 1. It is not the set condition. Okay, it is not set condition, it is actually the inactive mode. Okay, and here this one is the set condition. Okay, so here you can see that clock is 1, so that means the flip-flop is in active mode. Okay, and you have 1 and 1, sorry, 1 and 0, that means that is set condition. Okay, 1 and 0, you have set condition. Okay, so you have set the pin to 1. Okay, so this is the characteristic table for level triggered active high JK flip-flops. Okay, please okay, please compare this with the table. Okay, I hope uh, my logic is correct. Okay, anyway, my logic is correct. Okay, but maybe if I have done a mistake, uh, you can uh, you can note this. Okay, you can note that, you can compare this table with the characteristic table in your reference book. Okay, so I hope the characteristic table should be there. Okay, otherwise you can in the internet also you can find it. Okay, so please uh, compare this uh, with another table. Okay, and please try to do this by yourself. Okay, then you can you can refresh your mind again. Okay, refresh your memory again. Okay, so that is level trigger. Okay, and what is edge trigger? Okay, what is edge trigger? Okay, so here we have created the truth table or characteristic table for level triggered active high JK flip-flops. Okay, so you can search it in the internet and you can directly get the table and you can compare. Okay, so I think it should be okay. Okay, if I have done any mistake, please inform me. Okay, then I can correct it. Okay, so actually these are not intended to do here. Okay, I am just refreshing your memory. Okay, okay, now this is edge. Now we need to talk about edge triggered. Okay, so what is edge triggered? Edge triggered. Okay, so in the interaction session, okay, I told you that there is a subject called triggering. Okay, triggering. Okay, so when we are using oscilloscope, you have to use this trigger theory. Okay, this triggering process. Okay, I have already told you that in our oscilloscope we have an internal trigger capability. Okay, so if the signal is given, it is internally triggered and we can see the waveform. Okay, but some oscilloscope are not uh, self triggered. Okay, we have to give the external trigger to activate to trigger the given signal. Okay, so I have told you that there are three type of triggering. Okay, one is uh, using extract clock. extract clock triggering, another is a self triggering. Okay, self triggering, another is a separating triggering. Okay, so you can refresh your memory. This is for just for your knowledge. Okay, okay. So I recommend you to search about the triggering. Okay, circuit triggering, and find more information. Okay, so those will be important. Okay, for your study. Okay, but for this course we are not talking about the triggering. Okay, so for the exam you will not come these things. Okay, but for your knowledge you can see this. Okay, because we are when we are using digital circuits or digital instrument, these are usually we uh, use. Okay, so it is better to have idea about this. Okay, so what is edge trigger? Okay, so we have told you that the edge triggered. Okay, edge triggered the flip flops. Okay, flip flops. So in level triggered, you know that active and inactive mode. Okay, is defined using the clock level. Okay, using the clock level. If the clock level is 1, it is in active mode. Okay, if the clock level is 0, it is not in active mode. Okay, it is in inactive mode. Okay, so in clock triggered, we define or we change the status using the level of the clock. Okay, but this edge triggered means we change the active and inactive mode using the edge of the clock pulse. Okay, what is the edge of the clock pulse? Okay, so you know that this is the clock pulse train. Okay, and you know that these are the edge. These are the edge. Okay, so this is actually rising edge. This is the rising edge. Okay, this is the rising edge, and uh, this will be the falling edge. Okay, so this is the falling edge. Okay, this is the falling edge. Okay, this is rising edge and falling edge. Okay, so these are the edge. What is edge trigger means? In level triggered, okay, uh, the flip flops is work according to the level. Okay, but in edge triggered, flip flop is work or active according to this edge. Okay, according to this edge. Okay, so you can see that this is the rising edge and this is the falling edge. Okay, so there are two basically edge there, no, rising edge and falling edge. Okay, so we have two type of edge triggered. Okay, one is at rising edge. Okay, other is an falling edge. Okay, rising edge and falling edge. In rising edge, we called it positive edge triggered. Okay, positive edge triggered. In falling edge, we called it negative edge triggered. Okay, edge triggered. So you can see that here the flip-flops is active when the clock pulse is transformed from low to high, from low to high. Okay, in positive edge trigger, it is in rising edge, that means low to high. Okay, and if it is negative edge triggered, okay, the flip flops will trigger in falling edge. Okay, so that means it is at the point the clock pulse transform from 1 to 0, that means high to low. Okay. So the summary is, if it is positive edge trigger, the tip tops will active or deactive at low to high, actually active, okay, active at low to high edge, okay. And if it is negative edge trigger, the tip tops is active at high to low edge, okay. So that is the idea you should have, okay. So uh, so I think these things you have to know, okay. So if we consider our, clock edge is stable, okay, clock is stable, okay. If we consider our table, so what is this table? What is this table? This is characteristic table for active high, active high clock triggered, active high clock triggered JK flip-flops. Okay, active high clock triggered, sorry, level triggered JK flip-flops. Okay, flip-flops. Okay, so if you consider this, okay, if you consider active high, okay, active high edge triggered JK flip-flops, edge triggered JK flip-flops, okay, JK flip-flops, there is no any change of these things, okay. Only the change is, you can see that, so here these are the active points, okay. Clock is 1, the active points are these, okay, okay, these are the active points, okay, these are the active points, because at that time the clock is 1, okay, in clock triggered, in level triggered, okay. So instead of this level, okay, if it is edge triggered, this happen at the edge, okay, this transition happen at the edge, okay. So that is the word actually, this transition happen at edge, okay, at edge, okay. So if it is positive edge, if it is positive edge triggered, okay, if it is positive edge triggered, okay, if it is positive edge triggered, this transition happen, okay, this transition happen at the positive edge, that means high to low, okay. So this happen at the edge, high to low edge, okay, high to low edge, like this, okay. That means at the rising edge, okay, this is at the rising edge, okay. Transition happen at the rising edge. So rising edge I denote as like this, because it is increasing, level is increasing, low to high, okay. So I put an arrow to the increasing side, okay. So this is, so if you just put a arrow instead of this one level, okay, so this will be the characteristic table for positive edge triggered active high JK flip-flops, okay. And what if I put the arrow to this side, this side, okay, think what happened, okay. If I put the arrow to this time, this side, that means the transition happened at high to low, high to low transition, okay, high to low edge, okay. So that is for negative edge, no, that is for negative edge trigger, okay, that is for negative edge trigger, okay. For negative edge trigger, what I have to do, I have to simply put these active points. I have to simply map this active point to the negative edge point, to the negative edge. That means to the falling edge. Okay, falling edge means low to high. Sorry, high to low in this direction. Okay, correct. So I think you have got the idea. Okay, so we will do some work. Okay, then you can you can uh, again clear the doubt points again. Okay, so we will try to do some example, one or two examples. Okay, uh, so in the interaction session I have given you a example. Okay, so you can so we will try to do that one. Okay, we will try to do that one. So again I will so again I should uh, tell you that, okay, you have to have this basic knowledge, okay, before starting the study on counters and registers. Okay, so please refresh your memory. Okay, so this is just to refresh the memory. Okay, so you know that we have flip-flops. Okay, we have flip-flops. uh, I think you have already maybe learned that flip-flops are actually nothing but multi-vibrator. Okay, multi-vibrator. Okay, so these are maybe monostable vibrator, multi-vibrator, or stable multi-vibrator. Okay, so maybe you have learned these things in your past module. Okay, but for this time we don't need that knowledge. Okay, we no need to realize the flip-flops as a multi-vibrator. Okay, but if you forgot these things, you can refer the reference book can refresh your mind. Okay, but these are not going to ask your examination. Okay, this is for your knowledge. Okay, but you need to have the basic knowledge. Okay, what are the flip-flops, type of flip-flops? Basically we have RS and JK flip-flops. Okay, and we have clock flip-flops. Okay, so when we are talking about clock flip-flops, we are talking about level triggered and edge triggered flip-flops. Okay, so these are the block diagram for edge triggered flip-flops. Okay, and for level triggered flip-flops. Okay, level triggered flip-flops, uh, the notation is somewhat difficult. Okay, somewhat different. Okay, so for level triggered, actually, okay, the same thing. Okay, for active high, it is like this. Okay, active high, it is like this. Okay, you have the output. This is JK. So this is RS. Okay, this is RS. Okay, and uh, so so this is RS. Okay, and this is active high. If it is level triggered, active high level triggered, we just put the clock at as itself. Okay, we are not doing any change. Okay, but uh, if it is edge triggered, if it is edge triggered, okay, if it is edge triggered, what we have to do, we can't put this clock at itself. We have to put the edge trigger circuit here. Okay, we have to we have to we have to put the edge trigger circuit, edge detection, actually edge detection circuit. detection circuit to this clock pin. Okay, so these are we have talked these things in our interaction session. Okay, so I think you can understand these things. Okay, so basically we should have two types of edge detection circuits. One is positive edge detection circuit. Okay, edge detection circuit, and other is negative edge detection circuit. Okay, the positive edge detection circuit will be like this. Okay, so it is a simple circuit actually. You can use an AND gate to implement this positive edge trigger. Okay, positive edge detection circuit. Okay, so it is look like this actually. Okay. So if you put a clock here like this, okay, so here you have the inverted one like this, okay, and here you have the same one like this, okay. So this signal is going through a NOT gate, okay. So there is a propagation delay, okay. So if you write these two signal, okay, in the same timeline, okay, in the same timeline, you will have this kind of waveforms, okay. So this is the clock input, the signal here, okay, and the signal here is somewhat delayed, okay. So this will be like this, and it is inverted like this, okay. So you can see that it is delayed somewhat, okay. So you can see that, okay. I will write it more clear, okay, okay. Sorry. So you can see that here you have a pulse like this. Okay, here you have the clock pulse like this, here in this point, and this point you have a inverted pulse, and it is also delayed. Okay, you have an inverted pulse, and it is also delayed due to the propagation delay of this NOT gate. Okay, like this. Okay, and you can see that here, if it is starting at T0, this one is started at T1. Okay, so there is a delay, no? T1 minus T naught delay. There is a delta T delay. Okay, and this delay is there also. This delay is there also, delta T delay. So this delay, okay, so you can see that this is 1 and 0. So you will have a pulse at this point, okay, like this. Okay. So if delay is very low, that means if the propagation delay of this NOT gate is very low, you have very narrow pulse here. Okay. So that is the detected signal actually. Okay, that is the detected signal. Okay. So this circuit can be used to detect the positive edge. Okay. And for negative edge, okay, negative edge, you can do a very little modification. Okay, so you have to put a NOT gate here also. Okay, okay, you have to put a NOT gate here also, like this, for the both cases. Okay, and this will be the clock, like this. Okay, and here you will have this kind of pulse. Okay, and try to get this pulse as a homework. Okay, so try to realize this by yourself. Okay, so you have to draw like this, the 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 corresponding pulses, and see how we can get this negative pulse. Okay, how we can get this negative pulse? Okay, so you can see that, sorry, so you will not have like this. Okay, you will not have like this. Okay, at the edge, I hope you will have a pulse like this. Okay, like this at the falling edge. Okay, at the falling edge. So you can see that here, this pulse is at, this narrow pulse is at the rising edge. Okay, and this narrow pulse should be at the falling edge. Okay, falling edge. So try to realize this by yourself. Okay. Okay. So this circuit should be employed. If it is edge triggered, or if it is edge triggered, this positive edge detection circuit or negative edge detection circuit should be employed to this flip-flops. Okay. So we are using this notation. We are using actually this notation to represent that one. Okay. To represent that one. To represent this circuit actually. Okay. So if the mark like this is there, it is edge triggered circuits. Okay. And this is actually for positive edge triggered. This circuit symbol is for positive edge triggered. Okay. And circuit symbol for negative edge, negative edge triggered will be, you have a dot here. Okay. So it will represent this circuit, negative edge detection circuit. Okay. It, this notation will be representing this negative edge detection circuit. Okay, detection circuits. Okay. So these are the circuit symbols for RS or JK. The symbols is same in any cases. Okay, symbol is same for any cases. Okay, so this will be the symbols. Okay, so this is for active high positive edge triggered, and this is for active low positive edge trigger. Okay, so as a exercise, I will ask to draw the circuit symbol for, okay, circuit symbol for JK flip flops. Okay, I am sorry. Okay, actually, these are SR flip flops. Okay, these are SR flip flops. All these things we are talking about SR flip flops, not JK. So I have mistake this name. Okay, so these are SR flip flops actually, not JK flip flops. Okay, so now I ask to draw you the circuit symbol for JK flip flops. JK, active low, negative edge triggered, and positive edge triggered. Positive edge triggered. Positive edge triggered. Circuit symbol for negative edge triggered, then positive edge triggered. Please try to do this by yourself. Okay. Draw the circuit or the circuit symbol for active low JK flip flops for negative edge triggered and positive edge triggered. Okay. Okay. Now we will talk about JK flip flops also. Okay. JK flip flops also. Okay. So JK flip flops is same circuit symbols are there. Okay, like this. Okay. And here it will be JK. Okay, if it is clock, you will have like this. Okay, so if it is negative, active low or high, you will have the same dot as we have discussed later. Okay, so this is for active high, active high clock triggered. Okay, active high clock triggered. sorry, level triggered. Okay, and if we draw like this, if we put not, if you put not gate for the input, okay, it will be active low, active low. So it will be level triggered again, active low level triggered JK flip-flops. Okay. Okay. So basically you should have the idea about you should have the idea about the function table of JK flip-flops. Okay. JK flip-flops. Okay. So you have J and K and you have Qn plus 1. Okay. So there should be 4 status 0 0 0 1 1 0 1 1. Okay. Okay. For active high, okay, for active high JK flip-flops, if it is 0 0, you have Qn. Okay, you have Qn. If it is 0 1, you have 0. Okay, that means this is the set. Okay, so this is the, sorry, reset, same as SR flip-flops. Okay, 0 1 0. Okay, and 1 0, if you have 1 0, you have 1 here. So this is set condition. Okay, and if it is 1 1, in SR flip-flops this is forbidden, no? In SR flip-flops this is forbidden. Actually that is the issue with the SR flip-flops. Okay, that is the issue. We can't have this combination. Okay, that is the issue. Okay, and this JK flip-flops will overcome that issue. Okay, so here in 1 1 also we have a status that is Qn bar. Okay, we have the bar. Okay, the inverse of the present input, inverse of the past output. Okay, so this is called toggle condition, no, toggle status. Okay, so this is the function table for active high JK flip-flops. And if you have this, you can easily draw the function table for Q n plus 1 here. Okay. Function table for active low also. Active low also. All these are toggle. No? Okay. So here if it is 0 0, okay. If it is 0 0, now it should be 1 1 QA. Okay. And if it is 0 1, okay, it should be 1 0. That is the reset condition. Okay. And if it is 1 0, here it should be 0 1. That will be the set condition. Okay. And if it is 0 0, here it is 1 1 toggle status, but here toggle is 0 0. So you have Qn bar. Okay. Here you have Qn bar. Okay. So this will be the toggle. Okay. Okay. I again recheck it. If it is 1 1, you have Qn. Correct. If it is 1 1, you have Qn JK. Okay. If it is 1 0, you have 0 reset. Okay. If it is 1 0 1, okay, if it is 0 1, you will have 1. Okay, 0 1, you will have 1. So that is the rest set condition. If you have 0 0, it is toggle. That means we have Qn bar. Okay, inverse of the past input. Okay, so this is the function table for active low JK flip-flops. Okay, and all the things we are discussed about the trigger, edge triggered and level triggered are same in this case, but you have to consider it with the function table. Okay. So now I think we can do an exercise. Okay. So we will use JK flip flops. Okay. So I think now you will have you have the basic idea about SR flip flops. Okay. Now you also have the basic idea about the JK flip flops. So you can you should have you should keep you should keep in memory that there may be two types of uh, clock flip flops, JK flip flops or SR flip flops, level triggered and edge triggered. Okay, and so according to that active and inactive mode, we have to we can write the present output. Okay, okay. So we will take a example. Okay, so this is the example I have get in the uh, uh, get in our interaction session, last interaction session. Okay, so we have a JK flip flops. Okay. We have a JK flip flops. Okay, we have a JK flip flops. Okay, and this will be the output. This will be the output Qn plus 1. Okay, and this is positive edge triggered circuit. Okay, so you have like this. Okay, so this is positive edge trigger. Okay, that means the variation happen at the rising edge. Okay, variation happen at the rising edge. Okay, okay. Now, okay, okay. Now we have a circuit like this. Okay, using this flip flops. Okay, we have a circuit like this. Okay, okay. So we have okay, we have like this. Okay, we have here we have Q and here we have Q bar. Okay, so this will be the output. Q will be the output. Okay, so Qn plus 1 will be present output. Present output. Qn will be passed output. Okay, Qn will be passed output. Okay, so and I have connected this like this. Okay, like this. Okay, so I am giving a clock signal like this. For this one, I am giving a clock signal like this. Okay, so I will draw the clock signal here. The clock signal is will look like this. Okay, now I am asked to draw you okay. Now I asked you to draw the waveform here. Okay, so we are given a clock like this, and we should have a waveform here also. Okay, now I am asking to draw the waveform here. Okay, so this will be the output. Okay, the waveform will be Qn plus 1. No? Okay, okay. Now let's say that at initially, okay, let's say that at initially this Q is 0. This Q is 0. Okay, this Q is 0, the output is 0 at the initial point. Okay, and and also Yeah. Okay. So so this is a JK flip-flops. Okay. So we need to have the knowledge. Okay. We need to use the function table. Okay. We need to use the function table. Okay. So what is the function table? Okay. Let's say that this is a, so you can see that this is a active high, no? Active high. How you identify it? Here there is no any dot. If we have put a dot here, it will be active low. Okay. So we need to have the function table for active high JK flip-flops. Okay. Active high JK flip-flops. Okay. JK flip-flop. Okay. So we can put, so I can't remember, I have to show it. Yeah, I have write it here. Okay. So if you have 1, 0, you have 1. So this will be the Qn plus 1. Okay. So this will be J, this will be K, and this will be the present input, Qn plus 1. Okay. Okay. And you have, yeah, 1, 0, 0, 1, 0, 0, 1, 1. Okay. If it is 1, 0, that is set condition 1. 0, 1, that is reset condition 0. 0, 0, you will have the Qn, same Qn. 1, 1, you will have the toggle input. That means Qn bar. Okay. So this is the function table for active low. So we have to use this. Okay. And we know that this is the edge triggered, and it is the right, the positive edge triggered. Okay. Because here there is no any dot. Okay. So this is a positive edge triggered one. Okay. So so you know that all these transition happen at this rising edge. Okay. So you can see that these are the rising edge. This one is a rising edge, and this one is rising edge. This one is rising edge. Again, this one is rising edge, and this one is rising edge. These are falling edges. Okay. At the falling edges, there is no any impact. Okay. The same output will be there because it is in deactive mode. Okay. Okay. Now we will see, we will try to draw this waveform. Okay. So you can see that now the Q is initially 0. Okay. The Q is initially 0. So here this port is 0. And you can see that this port is directly short circuited to J port. Okay. Directly connected to the J port. Okay. And the J also should be 0. And if this 0, the Q bar should be 1. Okay. And it is also short circuited to this port. Okay. So the K should be 1. Okay. So now you can see that J is 0 and K is 1. Okay. K is 1. Okay. Okay. Now what happened? Okay. So you see that now we have to draw this signal. Okay. Waveform. So you can see that from this point to here, it is, there is no any difference, no? Okay. So same Q is there, Q output is 0. Okay. So Q also will be there like this. Okay. And at the positive edge, there should be a transition, no? Okay. So here it will, so at this point it will become active one. Okay. So now you can see that at this point the J value will be 0 and K value will be 1. Again the output will be 0. Again at this point the output will be 0. So you will have 0 output. And this is a falling edge, no change. So you will have like this. Okay. And again here you can see that you can see that again J is 0 and K is 1. Okay. And there is a edge. Okay. Rising edge. So there should be inactive mode. So If it is 0 and 1 again, the present output also will be 0. Again, you will have a 0 like this. Okay. So you will have like this. Okay. So if this is set to 0, you can't see any waveform here. Okay. You can't see any waveform here. Okay. You have 0 voltage. Okay. So you can test this. Okay. You can test this at lab. Okay. You can get the JK flip-flops, and you can get a NAND gate and NOR gate, sorry, NAND gate and NOT gate. Then you can implement edge trigger circuit, positive edge trigger circuit, connect it to the JK flip-flops, and you can put a clock, and then you can do the wiring like this, and you can check this. Okay. So you will see that there is no output. Okay, the Q here, there is no waveform. It is like this. Okay. So now I want, okay, now I want like this. Okay, I want like this. Okay. So I want to initially set this Q to 1. I want to initially set this Q to 1. Okay. So let's see what happened. Okay. Let's see what happened. Okay. So you can see that. So now I am going to again draw this output waveform. Okay. Now we set Q to 1. Initial state is 1. Okay. Initial state is 1. Now I want to draw this. Okay. Now I want to draw this. Again. Okay. So in the same way, these are the rising edge. Okay. So the circuit will operate or active in these edges also. Okay. In these edges also, the circuit will be operate. Okay. So you can see this. Okay. You can see this. So I hope in next interaction session we can do this experiment. Okay. Okay. So 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 these are the negative positive edges. Okay, positive edges, rising edge. Okay, so we will see what happened. Okay, so this output is for what? The initial state Q is 0. Now we are going to draw the output waveform for initial Q state is 1. Okay, now if it is initially 1, this Q bar will be 0. Okay, if this is 1, Q bar will be 0. Okay, Q bar will be 0. Okay, now you can see that if the Q is 1, Q bar should be 0. So you can see that Q bar is directly short circuited to J pin. Okay, so this J pin also should be 1. Okay, the J pin also should be 1. Okay, J pin also should be 1. Okay, and you can see that Q is 0. Q bar is 0. If the Q is 1, Q bar should be 0. And Q bar pin is again short circuited to this pin. Okay, K pin. So the K should be 0, this value. Okay, this value. Okay, now we see from this point to this point, there is no any different. So we have the, sorry, there is no any different means. Okay, no any different means the Q is 1. Now we have 1. Okay, now we have 1. Okay, like this. Okay, now at the falling edge there should be a transition. Okay, now you can see that it is 1 0. It is 1 and 0. Now the present will be again 1. Okay, so it will be 1. at this point it will be turned to 1. Okay, now it is going like this. Okay, so this is 0 status and this is 1. Okay, and this is rise input, this is fall in edge, so there is no any difference. So it will go like this. Okay, it will go like this. Okay, and again we have a rise in edge. Now j is 1, k is 0, again you have 1. Okay, like this. Up to here it is same. Okay, so you have 1 1 1 like this. Okay, so here you have 0. Okay, here you have 1. Okay, and that means you have, if you set this 1 to 5 volt, you have a 5 volt here. So you have a direct signal like this. Okay, 5 volt or something. Okay, at the output you will have a continuous signal. Okay, continuous signal, the direct signal actually, DC current. Okay, 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 so that is the output. Okay, so you can check this. Okay, so I hope you get the idea. Okay, now I will give you two exercises. Okay, now I will give you two exercises. Okay, so one, okay, if this flip flop is active low, that means here I put 1. Okay, and if it is positive trigger, okay, and we have a J and we have a K here. Okay, and in the same way you have Q here and you have Q bar here. Okay, same circuit, only different is the previous one is active high, but this will be active low. Okay, that means you have to use the active low uh, function table to realize these circuits. Okay, and if you are given a circuit, if you are given a clock pulse like this, okay, you need to draw the output Q, the waveform here, according to this transition. Okay, according to this transition, you should have to draw the output waveform. Okay, so try to do this. Okay, try to do this. And again, if you are given, so this is for positive edge circuits. Okay, so this is your first activity. And if you are given a negative, if you are given a negative edge trigger, okay, so the second activity for the negative edge triggered low, active low. Okay, so please try to draw the signal for this one also, for the positive edge triggered and for negative edge triggered for active low flip-flops. Okay, so that is your homework. Okay, please try to do this by yourself. Okay, so in the next session we will discuss this. Okay, so thank you. Okay.